For this problem, we are looking at a bottle that has a mixture of liquids inside. Specifically, this is some kind of liquor. There's water and there's ethanol. And we'll assume that's really it. There's not much else. Well, these bottles have a bunch of liquid in them and a little bit of headspace for gas. And depending on the factory, you will usually fill a little nitrogen in that headspace. That way, you avoid oxidation, it doesn't go bad and become acidic. You want nitrogen because it's inert and does nothing with the mixture. And so the devices used to bottle usually fill it with a little dinitrogen at a higher pressure than outside. That way, the emphasis is on things going out, and so none of the outside air ever really leaks in. Granted, it should be sealed, and so no gas should escape, but if gas were to, it would go out instead of in. Well, this bottle was bottled at 25 Celsius. It has this pressure of the N2 was added, and then it shipped, and it's a summer day, and it's hot, and inside the shipping container, it just starts to swelter. And it gets up to 40 Celsius. They forgot they were supposed to have some refrigeration in this cargo van, and it shatters. The bottle heated up and exploded. It broke. Well, the temperature outside, so the temperature of the bottle as it got heated up, was 40 Celsius. The external pressure was 1 atmosphere. Despite what's in the bottle, the outside was just normal, taking the coast road in summer, so we're down at sea level. Well, these bottles have a strength. They're so thick with glass, and it's easy enough to test. It ends up, they shatter if the inside matches or exceeds 240 torr in overpressure. So if you're pushing out with 240 extra torr, the bottle can't handle it and it blows up. Using this info, we're going to find what the mixture is. We're going to find the percentage. What's the proof of this liquor? Now it seems a little odd at first. There's some mixture. Is this 20 proof, 40 proof, 80 proof? What is the percent mixture of this solution? This mixture of ethanol and water. And we can find it from the gas laws. What we have to realize, think back to vapor pressure. We'll use 2 colors here. There's some white dots and there's some green dots. Well, vapor pressure is all about particles evaporating, particles jumping out of the liquid. Well, if you have a container that is pure one compound, and you have a temperature high enough for 2 per second to escape, well, it will be the white material that escapes. But if you have a temperature hot enough for 2 per second to escape, well, the mixture is all the same temperature. All the particles have that energy. Some of the molecules at the surface are not the white molecule. Some of the times when 2 of the molecules at the surface have the energy to leave, one of them is not water, or one of them is not ethanol, whichever one the pure sample was. The idea means that if you're supposed to kick 2 per second into the gas phase, you're not, or at least not of the one compound. So we'll say the white ones are water. In a pure water sample, you would get 2 per second leaving, so that is the return rate you need to reach your vapor pressure. If my sample is a mixture of things, well, water just doesn't escape as often. And so what we find is that even if the total rate is 2 per second, the water rate is reduced. It becomes less than 2 per second because we have a little bit of the other thing escaping. The net effect is that your vapor pressure decreases for a mixture, specifically by its percentage. So whatever your vapor pressure is supposed to be, times that by the mole fraction of the thing, and you will get your vapor pressure actual. So we can find the mole fraction, and therefore reasonably the percentage alcohol content, if we can find the vapor pressures. So in this problem, that is our goal. We are going to find the vapor pressures of our liquids. Because why does our bottle shatter? Well, as it heats up, the gas that was in there starts bouncing around, but we also start introducing some water and some ethanol. And so we are increasing the total pressure in the headspace, raising the pressure until it explodes. Well, let's think about how to do this. The bottle explodes when it has 240 torr more internal pressure than outside. We said outside that day was just 1 atmosphere, which is 760 torr. Well, I need my inside to be more than that. I have my bottle. It's got 760 outside. Trying to crush it, I need 760 plus the 240 before the bottle will explode. And so I can find that my inside, my pressure inside, must be 1,000. My total internal pressure must be 1,000 torr for it to push out hard enough to overcome the outside pressure and explode the glass. So I know my inside. I know that 1,000 torr must be my inside pressure. Well, what are all the things that make it up? Well, there's the pressure of the gas, the N2, that was originally in it. And there's the vapor pressure. Well, we're getting vapor pressure from 2 different liquids, both the water and the ethanol. So all we'll know for certain is the total vapor pressure for now. But let's see what we can do. So if we go look back up above, it was originally 25 Celsius with an N2 pressure of 836.7 torr. We get it up to 40 degrees Celsius. Well, it's going to have some new pressure at that higher temp. We don't have a volume for the headspace, so we're not able to calculate out the moles of the N2, but we really don't need to. The gas isn't going anywhere, so the moles should be the same. The volume of that headspace isn't changing. The bottle's not changing its size. So really, we just have pressure and temperature. I know pressure 1 and temp 1, and I know temp 2. We can solve for pressure 2. So if we want to find the pressure of N2 at 40 degrees Celsius, well, my temperature, 40 degrees Celsius in Kelvin, so 313.15 Kelvin, must equal my original 836.7 torr over my original 25, so 298.15 Kelvin. Rearrange, I can find what my pressure of nitrogen must now be up to. 836.7 divided by 298.15 times 313.15. 878.8 torr. So we know the pressure of N2, it had definitely not gotten anywhere near enough to explode the bottle yet. The remainder, though, must have come from my vapor pressure. And so we can edit in, we can say, hey, 878.8, or plus the vapor pressure, must equal 1,000. What we'll find then is that if we subtract them across, our vapor pressure total must equal 121.2 torr. So we can actually just find the vapor pressure in the bottle. Well, let's think about that vapor pressure. Our vapor pressure total is going to be the vapor pressure actual of the water plus the vapor pressure actual of the ethanol. Since it's a mixture, it's not the pure amount of either. Well, we were told it for water. At 40 degrees Celsius, the vapor pressure for water, so the pressure of H2O, and we'll introduce a symbol naught. The pressure naught for water at 40 Celsius means the pure, if it's just the water, if nothing else. This was 55.3 torr. And the pressure of just pure ethanol at 40 degrees Celsius, we said was 220 torr. Well, they're not pure, so we need to multiply them by the mole fraction. So we can rearrange this a little bit, clean it up. We know that X of water, so the mole fraction of water, times what its vapor pressure would be if it was pure, plus the mole fraction of ethanol, ETOH for short, times what it would be, 220 torr, if it was pure. All that has to equal our vapor pressure total. 121.2 torr. Well, at the moment I have two variables. You can't solve a problem with two variables, so we have to think for a second. How do we get this down to one variable? Well, remember mole fraction. The total mole fraction is just all of it. So 1 must equal the sum of all the other mole fractions, however many you have. Well, I only have 2. So 1 must equal the mole fraction of water plus the mole fraction of ethanol. If there are only 2 things in there, they must add up to 100%. Which means we can rearrange, just subtract one of these. 1 minus the mole fraction of water must be the mole fraction of ethanol. Which means I can replace the mole fraction of ethanol with a variable we already have in the problem. 121.2 torr must equal the mole fraction of water times 55.3 torr plus 1 minus the mole fraction of water times 220 torr. Multiply those, 55.3 torr X of water plus 220 torr minus 220 torr X of water must equal 121.2 torr. Rearrange a little bit. What we'll get is negative 98.8 torr must equal negative 164.7 torr X of H2O. So subtracted 220 off both sides, and then 55.3 minus 220 to get our right side. Well, they're both negative, so times by -1 to get them both positive. Divide 164.7 torr on both sides to get the mole fraction on its own. X of H2O is going to be 0.59999 0.60. It is 60% water. We said earlier ethanol is 1 minus, so 1 minus 0.6. for 0.4 for the X of ethanol. This mixture was 60% water, 40% ethanol. It's 80 proof. Your proof is double your percentage. So we had a bottle that had some pressure in it, and then as it got hotter, the pressure of the gas increased and some vapor pressure increased. The bottle eventually exploded. We were able to use the pressure change of the gas, of the dinitrogen, to say, well, how much vapor pressure must have been in there to cause this bottle to explode? And so we found that, well, if there must have been 1,000 torr internal pressure in order to overcome the external pressure by 240 total extra, then the vapor pressure necessary to do it was 121.2. Knowing what our vapor pressure must have been, we can then set this equation that says, hey, if 100% of it was water, it would have been this pressure. If 100% of it was ethanol, it would have been this pressure. Take the fraction of each of those that the liquid represents. And so we simplified, solved down, and found our percentages.